All right, we're still reviewing concepts related to magnetics, right? So the first one is magnetic field intensity. Feel free to interrupt anytime, okay? If you have any questions while I'm going through these materials, go ahead and interrupt me. Go ahead and turn on the microphone and interrupt me anytime, okay? All right, magnetic field intensity. Symbol is H, right? Capital letter H, and the unit is A over M, amperes over meter, right? And a magnetic field is created around a current carrying conductor. That's what we learned, right, from physics. If you have current carrying conductor, such as this one right here, this figure that I have right there, right? Current is flowing from right to left, and then using your right-hand rule, right? You know that there's going to be a magnetic field around or produced by this current, right? And the magnetic field has a direction, right? It's a vector, so it has a magnitude and direction, right? And again, if the current comes, direction of the current start from the right and to the left, then the magnetic field should be counterclockwise, right? And then magnetic force field is a vector, as I said earlier, perpendicular to the current. So if I were to redraw this to, hang on a second here, to front view of this figure, and imagine this is the cross-sectional area of the wire, right? Oops. And then current is out of the page, okay? Then again, right-hand rule, right? Then if I pick just one point outside of the wire, then at that point, right, we're gonna have magnetic field, right? And that magnetic field, let's see, magnetic field will be perpendicular to this, to the current. So let's see, and the direction should be this way, right? Following right-hand rule, right? And then in terms of the magnitude of the magnetic field at that point right here, right? If I pick, more points around this wire, the same distance as, let's say I call this point A, right? I pick another point that has the same distance from the center of the wire. I assume this is a perfect circle, okay? Something like this. Then at any point on that circle, right? At any point, you'll have magnetic field that has the same magnitude. Direction of course, going to change, right? Has to be perpendicular. So this one's going to be that way. At that point, it's going to be this way, and so on and so forth. Okay. So magnitude is the same, but the direction should change, right? Because it has to be perpendicular to the current itself, right? Okay. If several current carrying conductors passed, that's the first one. That's supposed to be pass. Is that right? That should be passing through, right? Or something like that. If several current carrying conductors passing through the enclosed area, circle in this case, the sum of currents must be included in the calculation of I net. So, depending on the number of wires, if you have more wires inside the circle, right, then you have to take into account the current on that other wire as well when calculating the strength of magnetic field at different points along that circle, right? So that's something that you also learn from physics, right? That's going to be the net current enclosed by this circle, okay? The magnetic field intensity measures the strength of magnetic field and is defined by the currents within that field, as I mentioned earlier, right? Again, that's net currents. Magnetic field intensity of any conductor configurations may be calculated by how do you say this, Biot-Savart law. I believe that's how you pronounce it. The Biot-Savart law is an equation that describes the magnetic field created by a current carrying wire and allows us to calculate the strength at different points outside of the wire, right? And this is analogous to Coulomb's law for electric field, right? So for electric field, you use Coulomb's law. For magnetic field, you use Biot-Savart law. And then derived from the Biot-Savart law is what we call Ampere's law. So again, this is just a refresher. This is one way to derive the Biot-Savart law is by starting with the equation for electric field, Coulomb's law, basically. Right? This is a Coulomb's law equation right there. The electric field is equal to, at any point around a charge point, right? You learn it from physics, right? You have a charge point, right? That could be plus Q minus Q. Then you can calculate the strength of the electric field at any point from that charge point, right? And that equation is that equation right here, where K is a constant, some constant, and then R is the distance, right? Between the distance between the charge point to the point of measurement, right? So starting with an expression for an electric field around a point charge Q, distance of R based on Coulomb's law, we have this equation right here, right? E is equal to K times Q over R squared. And then for magnetic field, we don't have a point of charge, right? What we have is current, right? Remember, we are trying to calculate magnetic field strength around a wire. So you have a conductor or a wire that's carrying current. So now we don't have any more point charge, right? What we have is wire, right? Some wires that's carrying current, right? Okay, so how do you replace a point charge with a conductor, current carrying conductor? Right? So rather than having a point charge, we do what we call a slice of this conductor, right? So take a slice of this conductor, something like that, right? Right? And then unlike, so that's the first thing, right? You take a slice of this, and of course the length of the slice will be di, right? Or actually dl, not dl, right? And then we have the current I, right? So therefore you have I dl, and then this chunk right there, unlike electric field, right? Electric field radiates its field, or not electric field, sorry, charge, right? A point charge radiates its field all around it, right? The direction is all around it, or it's going to all directions, I should say, right? For a point charge. For a chunk of conductor that has current I, it has a particular direction, right? It's not going all over the place, right? Unlike a point charge, right? For this picture, for example, that direction is going to be that way, right? Only, that way only, because current is flowing that way, right? So therefore this quote unquote point current, right, is going to have one direction instead of, radiating all over the place, okay? So we substitute Q with IDL. I is always constant in the wire, and DI makes it a point current element or current segment, basically treating this little chunk of the wire as our charge, right? We also exchange E with dB. So yeah, we don't have any more electric field, right? Now we are trying to calculate magnetic field outside of this wire, right? Since this is related to the current through a certain length, delta L, therefore the magnetic field will also be, would correspond to the change in that, or the distance for that little chunk right there, right? So dl corresponds to dB, okay? So now instead of E, now we have dB, right? So then the equation, the Coulomb's equation now becomes dB equals to K IDL, sorry, over R squared, right? Okay, and then K in Coulomb's law, right, in this equation right here, K is equal to 1 over 4 pi epsilon naught, and epsilon is our permittivity, right? Permittivity of materials right there. But for magnetic field, we don't use permittivity, but we use permeability, which is mu naught. And mu naught is the inverse of permittivity, like that, right? So therefore, if you replace epsilon naught with mu naught, right? Just go ahead and replace epsilon naught with 1 over mu naught and put it into this K, then you get a new equation now that states that dB is equal to mu naught over 4 pi IDL over R squared, right? And so that's the basic of Biot-Savart law right there, okay? And let's apply this equation to the following figure. So let's say this is our conductor right there. Current is flowing through this wire. And then again, we take a little chunk of this wire, right? We call it point current, if you will, right? Instead of point charge, point current, but this point current has a direction, right? And that's your delta L right there. And then there's the point of interest where you measure magnetic field, right? And since the strength of the field is the strongest or max when this angle is 90 degrees, so therefore this function should be corresponding to a sine function, isn't it? Right, sine of 90 degrees is 1. So therefore, to complete the equation, you introduce sine of theta right there. So now the equation becomes dV mu naught over 4 pi IDL sine of theta over R squared, right? And then we know that magnetic field, this is actually flux, right? Flux density. Magnetic flux density is equal to mu naught dH. H is what we are looking for, field intensity. And so therefore, dB is equal to mu naught dH. I'll go ahead and replace that with this, right? And what do we have? The mu naught cancels, right? So then you have dH equals to I sine theta dL over 4 pi R squared, okay? And that's why, yeah, unfortunately my L looks like an I here. That's something that I need to fix as well. Sorry about that. So the field intensity H is therefore, yeah, so now you can just take integral of both sides, right? With respect to the length of the circle, basically the point of interest, right? So that's, what do you call it? Circumference, right, of the area that you're interested in measuring the field, right? And so that's why you have these symbol right there, right? So you have to take the surface integral of, or loop integral of H dl, which should incorporate all the sign components inside that conductor, right? So there is the Biot-Savart law, right? And then when you simplify that into this equation, then you get Ampere's law, okay? That the loop integral of H, a closed loop integral of H with respect to dl, it should be equal to the net current within that loop, within that closed loop, okay? Again, H is a magnetic field intensity, right? Amps per meter. And if there are n number of conductors within that closed loop, then I net becomes n times I, and I should say that n conductors, each carrying current I, so that's gonna establish the I net, right? So then I net would be N times I. If you have N conductors and each is carrying current I. Okay, okay, any questions so far? So that's our equations for N conductors with each carrying current I. And this is, of course, equation that will be useful when we deal with transformers, inductors, because we use coils, right? We use coils, X number of turns, right? And each winding, of course, carrying the same current, right? So that's why I need to show this equation again from your previous class. I'm sure you've seen it before from maybe 255, right? Okay. Example 1, find H in a rectangular core, assume equal cross-sectional area around the core. So that's what we have here, right? So now we have this coil, right, has n number of turns or winding right there, right? And we want to determine field intensity around this point right there, right? There's going to be many fields, many what do you call it? Many H values. So what we want to calculate here is pretty much the average field intensity around this loop, right? As you know from that equation, the further away you are from the further away the point of measurement is from the current, from the wire, the less the field, right? Right, so that's something that we need to keep in mind, right? So the field strength is stronger here than there, for example, right? Okay, okay. So then let's see. So how do you calculate the field intensity for this example, right? Yeah, again, you have n number of turns, current flows that way, right? If you use the right-hand rule, then flux inside the core would flow upward on the left leg of the core, right? And then there's the cross section area of the core. And so again, you're applying that same equation, the Ampere's law, right? H times dl, the integral of H with respect to dl is equal to I net, right? There, now that one I use L. Okay, so the closed loop path, in this case, if you look at the geometry of the core, right, which L do you use, right? Because there's infinite numbers of L, right? There's infinite number of loops, right? You can have the outside of the core, that's one loop right there, right? The outside edge, right, of the core, that establishes one loop. Or you could also use the inner, right, edge of the core right there to define the loop, right? And then anything in between, right? There's infinite number of them. And so for this kind of situation, the way to find intensity is by kind of taking the mean path length, right? Kind of the average length of the loop, right? So that's by taking the average of basically the what do you call it, the width and the length of the core, okay? So something like this. So the one that I drew as a dashed line, that represents the mean path length of this problem, okay? So that gives you a good approximation of the field intensity for this problem. So the closed loop path is approximated by the mean path length, L of C, around the rectangular core. So therefore, the left-hand side of the equation, right, becomes just H times LC, right? And then the right-hand side of the equation, I net, that's n number of conductors, right? And each is carrying I, right? Each is carrying current I, okay? So therefore, I net is equal to n times I. So now that equation right here becomes H times LC equals n times I. And from there, I could approximate H to be n times I over LC, right? Now keep in mind that magnetic field intensity is proportional to I. We'll come back to this later, right? Very important for us to recognize this because we are EEs, right? We speak in terms of current and voltage, right? And H is magnetic field property, right? And I is current property, right? That's the property of our circuit, which is the windings, right? But as you can see, magnetic field property is related to electric circuit property I. That's convenient for us, SWEs, okay? So changing I, if you leave N and LC the same, and typically that's the case, right? You will already design your, you already have, for example, inductor with a fixed number of turns and the geometry of the core, right? You pick a core and you're, you know, you're going to be stuck with the same LC, right? So typically N and LC will be constant. And so how do you adjust the field intensity? Is by adjusting current, right? Current that you inject into this winding, okay? All right, so then the next example, finding H in rectangular core, but now I'm using numerical values, right? I'm using numbers now in the example. Now you see I have 10 amps flowing, right, injected into these windings. And there's 100 number of turns, so N is 100. And then the geometry of the core, as you can see, right, that's 2 centimeters right there, and they looks like they're symmetrical, right, all around. 10 centimeters around here, from here to here, from this point to that point, from that point to that point. So you can see they're symmetrical, right, all around. So that's good because that will make it easier for us to calculate the mean path, you know, length. Okay, so then we just apply that equation, same equation, H times LC is equal to N times I, right? H is what we're looking for, LC is the mean path length. So mean path length would be the midpoint basically, right? It's this length right here, right? The one that I use dotted lines right there, right? So our task now is to calculate the length of this loop right there, right? So if you look at that picture, you can see that the length of this side, for example, from here to here, that's going to be 10 plus 1 plus 2 times, so 10 centimeters, okay, plus 2 times 1/2 of 2, right? Because there's 2 right here and there's 2 right there, and we're taking the midpoint of that. So that's midpoint of 2 is that's what I'm writing here, 1/2 times 2. But then you multiply by 2 because there's 2 of them, 1 and 2. And so that would give us what? 12, isn't it? Right, so 12 centimeters from one side. Okay, you agree? So then for all 4, because we need 4, right? 1, we need to include all 4 sides. 1, 2, 3, 4, they're the same, you know, symmetrical structure. So therefore you have 12 here as well, 12 over there as well, and 12 over here as well. So 12 times 4, that should be 48 centimeters for the LC right here, right? And there's right there, 48 centimeters. You have to convert it into meters, okay? And so I have LC, which I just calculated to be 48 centimeters, N is 100, I is 10 amps. So the only unknown is H. So then from there, I know that the average field intensity inside this core would be 2083.3 amps per meter, okay? Any questions on this? Okay, then that's H. Right, that's field intensity. Another magnetic property is flux density. So H is field intensity, B is flux density, right? So how much what is the amount of flux per given area of the core, basically, right? So if you go back to this, for example, right, there's the section cross-sectional area of the core, right? And then flux density refers to how much flux is contained within this area, right? That's what B is. Of course, that's going to be related to flux intensity, right? Flux intensity, field intensity. The stronger the field, right? The stronger the field, then for the same amount of area, the stronger the field, the bigger the flux density, right? So therefore, the two are related, right? That's how they're related, right? Exactly, is that B flux density is equal to mu times H. Okay, what is mu? Mu is magnetic permeability of material. So every material will have mu, just like every material will have epsilon naught, right? So same thing here. The unit for mu is henries per meter. The unit for B for field density is Tesla. Okay. These are all SI units. Okay, we'll talk about units later, but these are all Tesla and henries per meter. These are part of SI, standard international units. Okay. Mu by itself, permeability is equal to mu r, can be broken down into two terms, mu r and mu naught, right? So we can represent mu, right, to be a number relative to permeability of vacuum or free space, right? So permeability of vacuum or free space is equal to 1. Oh, sorry, it's equal to 1. It's equal to, not 1, it's equal to this number right here. 4 pi times 10 to the minus 7, right? And so if a material has the same permeability as the free space or vacuum, then mu r will be equal to 1, right? So if mu r is equal to 1, that means its permeability is equal to permeability of free space or vacuum, right? And again, mu naught is equal to 4 pi, is a constant, 4 pi 10 to the minus 7 henries per meter, or roughly is equal to 1 over 800,000 henries per meter, right? So permeability, more on permeability, mu r, is the ability of a substance to acquire high magnetization in relatively weak magnetic field, right? So the higher permeability, the easier it is for us to establish magnetic flux inside that material. Right? That's what it means, right? So material that has high permeability means that that this is going to be a good material for us to use for inductors or transformers. Okay. You only need the physical implication of that would be that it only requires a small amount of current, right, to create strong magnetic field, or in this case, strong flux, right? If permeability is high. Okay. Magnetic flux, right? That's another property. Oh, hang on a second. Did I miss something here? No, okay. Okay, so then moving on to magnetic flux. Phi is equal to area integral of B times dA, right? So that would actually depend on the angle that the two makes, right? So if you have a unit area and you represent this unit area as a vector right there, right? Okay, and then if the flux density, let's say, is pointing, for example, that way, right? Then the strength, another strength, then the flux will be related to this angle, right? The angle that the two vectors make, right? So then just like the field intensity with the current carrying conductor, right? The strongest or the maximum strength, right, for current carrying conductor to field intensity happens when the angle is 90 degrees, right? So it's this one, right? So the maximum flux can be produced if flux density and the area vector is perpendicular, 90 degrees, right? So if that's the case, then the amount of flux, right, that flows through this area, right, the amount of flux that flows through this area is equal to B times A. Okay, so that will be the maximum that you can get if they are perpendicular. So if this is A, right, vector, the area vector, and this is the B vector. Okay. Any questions so far? So now we just reviewed 3 different magnetic properties, right? Field intensity. What else? Flux density, and then flux itself. Okay, and the unit for flux is Weber. That's the SI unit for flux. Okay. Determining the direction of flux in a coil. So use the right-hand rule, right? Oops. Okay. So if you look at this picture right there, direction of coil winding is the same direction as the other fingers, except for the thumb, right? So if you're folding your 4 other fingers, except for the thumb that way, then you can see that's that would follow the direction of the winding, right? So fold the 4 fingers in the direction of the winding, and then if you unfold your thumb, right, upward, then that would give you the direction of the flux. Okay. You should already learn it from physics. Now, we already applied that actually, right, in the previous example. Let's just go to this previous example. Yeah, see, yeah, for this one right here, yeah, you can see that the direction of the winding is going into, right, into and then out, right, into and out. So you can see that go ahead and curl your 4 fingers, except some of the 4 fingers, except for the thumb, into the direction of the windings, and then go ahead and unfold your thumb. Then the direction that the thumb is pointing at, that's going to be the direction of the flux in this area right there, in this leg right here. So that should be upward. You agree with that? So the flux should be going upward on the left leg. So then it's going to go clockwise around this structure, around this core. Okay. Now what's interesting is that if you apply that, right, into a coil like this, right, you can see clearly why having a coil is preferable, right? Why is it that we use coil a lot in terms of electromagnets, right? And you can see clearly from this picture, hopefully, that if let's say that you zoom in, right, to this. Let's see if I can zoom in. Yeah, quality is getting worse, but oh no, what happened? Crash. Doesn't like it. Oh, there you go. Hang on a second. Let me check to see if my internet is okay. Still good. So if I zoom in right there, right, and that X means that current is into the page, right? So imagine that current is into the page, and so by using the right-hand rule, the flux around it would be going clockwise. Yes, going clockwise. Okay. Now, 2 things that are interesting to me here, right? The first one is that if I look at the bottom side of this wire, so this area right here, right? I'm going to erase that now. Yeah, focus on that area. Okay, remember this is a coil, right? It goes around and around that way, right? So for this particular wire, it's the same wire, but at that location, the magnetic field under that wire is pointing from right to left. It's basically this way, right? You agree? Yes. Now go ahead and look at the next winding, which is right here. Look at the next winding. Same thing, right? You have current that goes into the page, right? So therefore, same thing, just like the top one, right? Clockwise direction. You agree? Now, when it goes clockwise, look at the top side of this wire or above this wire. Look at this area right here, right? Take a look at how the magnetic field is being produced around that second winding. You can see from there that, oh my God, what's going on? Okay, you can see that the magnetic field is pointing from left to right that way, right? So then why is that interesting? Anybody? While I'm looking at this internet connection. Why is that interesting to know? Say it again.
Don't they like cancel?
Yes, they cancel each other, right? They cancel each other. So why is that good? Why is that good that they cancel each other? But what I'm trying to say is that since they are canceling each other, that means there's practically no magnetic field between this winding and the next one, right? My internet is lagging right now. So hopefully it doesn't crash. But between windings, not just from these two, but if you go to the next one, same thing from this winding to the next one, practically between windings, between turns, maybe, right? That's maybe the right word, is between turns. There are practically zero magnetic field if you look at this area right there. Right? It's practically zero magnetic field. You agree with that statement? Oh, yeah, see it crashed. In a second here. It just crashed. Hang on. Maybe because I zoomed in too much. All right. Okay. Did I still share the screen? No, wait, I'm not sharing the screen anymore, right? Okay. Can you see it now?
Yeah, I can see it.
I can see it.
Okay, sorry about that. So let me erase that. So this is good, right? This is actually beneficial for us, right? The fact that the area right here between the turns pretty much has no magnetic field means that the two wires, right, they're not coupled to each other. The two coil, they are not coupled to each other. If they couple to each other, then what? Then you have leakage inductance, basically, right? So you have some flux that are coupling each other. They're not supposed to be coupling, right? That would create more parasitics, basically, right? Parasitic inductance for this coil, right? And so this is a simple and effective way of canceling flux between windings, between turns right there, right? So again, the reason why, because then you don't have any flux coupling between each winding, right? If it does, then you're gonna have some parasitic inductance, right? That's not desirable, okay? Is that clear? The second thing is this, let me, okay, do this. So that's the first thing that's interesting to me. The second one is this. All right, so again, back to this wire right here. Oh, okay, it's not lagging anymore, good. Go back to the top wire, okay? If you look at the top wire, go ahead and look at the left side of this wire. So focus on this wire, look at the left side of it, right? And go ahead and take a look at how magnetic flux or magnetic field is pointing to. Right, go ahead and use the right-hand rule, or it's also drawn there, that the magnetic field, right, is pointing upward, yes? So pointing outward. Agree? Right? Okay, so now remember this wire is going around a core, right? It could be air, like this picture, right? So the core could be air, but right now, right, it could be any core, right? So imagine this wire is wrapped around a core, right? So now it goes to this side right here. Right, the other side. This is one side, the right-hand side of the core. Here's the left-hand side of the core, right? So that same wire, right? Same current, right? It's the same wire, the same current. So now go ahead and look at the current. So now the current, since this is a coil, if the current is entering the page here, on the other side, the current must be leaving the page, yes? You agree with that, yes? So then if you agree with that, then go ahead and apply right-hand rule around this wire right here. It happened again. Okay. Do you see the glitch, by the way, that I just had?
Yeah, your screen disappears.
Yeah. Now, how about now? You see the picture again?
Yeah, we see it.
Okay. Sorry about that. It's a glitch. I don't know what happened there. All right, so going back, so focus on the left one. Now go ahead and do the right-hand rule, and you can see that to the right of this wire, right, to the right of that wire right there. It's lagging again right now. Go ahead and determine the direction of the field, right? We know that's going to be upward as well. See that? Upward, right? So why is that important? Why is that good? Well, because again, we're going to place our magnetic material inside, right? And by having these, right, arrangement of wire form into a coil like this, what we are doing is we are effectively producing flux that are concentrating inside the coil, right? If you go inside, if you look at inside the coil, right, that's where we're going to place the core. The flux is the most dense, right, in the center of this coil. You agree with that? And that's good, right? Because that's why we're going to place our core. We're not going to place the core here. We're not going to place the core there. We're going to place the core inside this coil. In fact, we wrap this coil around, right, that core, right? So we are putting a lot of flux in the center of the core, right? And again, that could be achieved effectively by making a coil. Right, a simple arrangement like this, right? Now, before it was just a coil to you. Now you know why we use a coil, right? Why we are making turns, and of course, the more the turns, the more flux you would produce in the center of this coil. Isn't that cool, right? So now you see a coil differently after you seeing this picture, right? Right, and now, in effect, right? If you think about this, right, in effect, this is creating like mimicking, right? Like mimicking a permanent magnet, pretty much, right? If I draw a permanent magnet, right, then you can see that the highest density of flux is in the center of this, or within this magnet, right? And if this is the north and this is the south, right, then the field goes this way, yes? Just like that, right? The highest density is in the magnet bar itself, just like the center of this coil. Look at the field, exactly the same shape, right? If you compare the two. So having a coil wrapped around a magnetic material pretty much mimic a permanent magnet, permanent magnet bar, okay? Any question on this? So that's what's cool about this simple arrangement that again effectively put very high concentration of flux inside the coil. And then we can place the core, and now we can make use of the magnetic field more effectively, right? By doing it this way. Okay. Oh, what happened here? So many glitches today. All right, next. Okay, I've done that one. Done that one. Maybe I should zoom out a little bit. Okay, maybe it doesn't like me zooming in too much. It does it again. All right. What's next here? So we done this one. Okay. So next page. So now toroid, right? That's a toroid right there. And imagine if you have a core, right? Donut, shape core, and you wrap coil around it, and the resulting what do you call it? Magnetic component is called toroid, right? And this is one of the best way, right, to create inductance, right, or inductor or transformer is by using a toroid like this. Now you know why, right? Because again, anywhere in the center of this coil, you have highest density of the flux, and then between windings, right, pretty much they cancel each other, right? Field cancel each other, right? So it's again, effective and efficient way of using flux density or flux field intensity, I should say. Sorry, field intensity from magnetic component. Okay. The problem with toroid, right? This is again one of the best shape to use for inductors or transformers. What will be the disadvantage of doing this? Why is it that if having a toroid, how do you say toroid, right? Is one of the best way of giving us inductor or making an inductor or transformer, then why is it that we don't often see toroid being used? What is the physical drawback? Oh, I just give you a clue. What is the drawback of a toroid?
Is it the spacing between the winding?
That's not the spacing between the winding.
Maybe it's difficult to physically wind.
That's one of them. Yes. What else? That's one of them. It is more difficult to wind. That's why if you look at the different type of toroid core, one of them it's just like a donut shape, right? If you look at the cross-sectional area of that core, they're round, right? They're round, and some of them still round, like a donut shape. But if you take the cross-sectional area of the core, it's actually not round; it's actually a rectangle, right? And yeah, so if you have a rectangle shape, rectangle cross-sectional area of a donut shape toroid core, yeah, good luck. That's really tough to wind. It's easier for us to kind of make it like a perfect winding though, because you can apply force as you make the turn. You apply force, around the edges, right, to make it a good winding. But that would definitely make calluses on your fingers. What else though? So that's right, more difficult to wind. What else? Think about the dimension of this, right? Think about how do you connect this on the board, on the PCB? If you have a toroid, how do you connect it to a PCB? That's going to take a lot of space, right? If let's say you have a PCB right here, right? You either lay it down like this, right? In which case, it's going to take a lot of space. or you could stand it up, right? That way. You could do that as well. But if you do this, then the height is going to be the height of the product, right, of the entire board would be quite tall, quite high, right? So either way, it's going to take some space, right? And so that's why for some applications where space is very limited, having a toroid is not really practical, even though it is one of the best way to make an inductor or transformer. Okay, so those are practical implication of having toroid, right, in electrical design, is that it's taking up space. Okay, so there's always a trade-off, right? Unfortunately. Is that clear? Hopefully. Any questions on that? So only when the space allows, okay, you can look for the solution right here. Right. Direction of flux, right? That's just right-hand rule again. You can see if you have this example, where would the flux flows in this rectangular core? Is it upward on the left leg? Upward or downward?
Downward, right?
Down.
Downward, yes. Okay, very good. All right, next. Faraday's law of EM induction. Okay. More refresher here. Faraday discovered that if the flux linking a loop or turn varies as a function of time, a voltage is induced between its terminals. The value of the induced voltage is proportional to the rate of change of flux, right? So if you have a coil, open terminal, and then you apply varying flux into this coil, then across the open terminal of the coil, you're gonna get induced voltage. And that's how we use this concept, right, for transformers as well as for motors, generators mostly, right? So you have a transformer such as this, for example, right? And you have two coils, right? Typically, at least a transformer should have two windings like this, right? And then you apply power to one of the windings, right? You apply power. That way you have current, right? Right. So this has to be changing current, right? Like AC, has to have an AC component to it. And then that current will, let's say, will create flux, right? That would produce flux inside this core. And that flux passes through that winding, that second winding, right? And that flux will also be varying with time, because the current varies with time. Therefore, the flux that is being produced in the core will also vary with time, right? And that flux that varies with time passes through inside the second coil, right? So that's this Faraday's law, right? That once you have varying flux inside the coil and in the open terminal of this coil, later we learn how to determine the flux. Sorry, not the flux, the polarity of the voltage. Right now, I just assume that's a plus, that's a minus, but you have induced voltage because of this changing flux inside that second coil, right? Since we have induced flux across the second coil, if I connect that to a load, then what? Then I have current flowing through, right? Okay, so that's the basic of a transformer. Same thing with the generator, right? I won't go through it, but same kind of a concept applies in the generator, right? You have a moving part, right, which is the rotor. The rotor creates the varying flux, and then on the stator, you have the second coil, right? And then the second coil has an open terminal, so then you have an induced voltage across the stator terminal, right? And then once you connect that stator terminal into a load, then you get current flowing from this generator, right? So I like to think of a generator as having the primary side spinning. So imagine this primary side is spinning to create the flux, right? And then the secondary side is stationary, right? That's the stator. And then that creates the induced voltage, right? And again, connected to a load, then you get current flowing out of this generator. Pretty neat, right? All right. This law establishes the basis of operation of transformers, generators, and AC motors according to SI system. When the flux inside a loop varies at the rate of 1 Weber per second, a voltage of 1 volt is induced between its terminals. Right, so if it's 1 Weber per second, that's the rate of the flux going through this loop, then you should have 1 volt across that terminal. The voltage induced, right, across the open terminal, that should be N d flux dt, right? So the number of turns, this number of turns though, okay? That number of turns on the second winding, not that one, okay? Not number of turns that one, but this number of turns. Times d flux dt, that's gonna be the rate of the flux flowing into this loop, right? Into the coil, right? Or is equal to N times delta flux delta T, right? If the change is not continuous, then yeah, then you can do delta flux over delta T, right? E in is induced voltage and number of turns in the coil. The flux dt, that's the first derivative of the flux, which is basically this the slope, right? Or the slope of the flux with respect to time. And then delta flux, that's the change of flux inside the coil. Delta T is time interval during which the flux changes in seconds. Right. Here's an example. Let's say that I have a coil of 2,000 turns surrounds a flux of 5 milliweber produced by a permanent magnet. The magnet is suddenly moved, causing the flux inside the coil to drop uniformly to 2 milliwebers in 1/10 of a second. Okay, what is the induced voltage? So that's the picture right there, right? So imagine I move this flux away from this coil, right? And so that movement, right, from this position to the next position right there, let's say this is position number 1, this is position number 2, right? As you are moving this permanent magnet from position 1 to position 2, that would create a change in the flux, right? That change in the flux with respect to time, that would create the induced voltage, okay? Of course, when you first start, right, when this permanent magnet is just standing still, then there is no induced voltage at all. It's going to be 0, right? But then as you are moving it, as you are moving the bar, right, permanent magnet bar to the right to position number 2, then you'll see the voltage there, right? And then once this permanent magnet reaches its final destination, right, location number 2, and standing still again, then of course you won't see any more induced voltage. So only during the time when it moves from 1 to 2, okay? And that happens 1/10 of a second. So how do you, what is the voltage across that terminal right here, right? So you have 2,000 turns of coil, and that's the open terminal. The induced voltage will be N times delta flux over delta T, right? N is 2,000, and delta flux is 5 to 2, because it drops, right, from 5 to 2. Is that right? Yeah, it is 5 to 2. I'm just double checking. See, I don't have any typo there. So 5 minus 2, and then delta T is 1/10, right? 1/10. So then you get induced voltage of as much as 60 volts across that terminal, okay? Just for that brief moment. And that's the max induced voltage you get. Any question on that? All right. So here it is. How do you determine the polarity, right? We have induced voltage. Well, which one is going to be the positive? Which one is going to be the negative, right? So there's this next section, Lenz's law. The direction of the voltage buildup in the coil is such that if the coil ends were short-circuited, it would produce current that would cause a flux opposing the original flux change. So I'll just do 3 steps here, right? I'll just present it into 3 steps to determine the polarity. First, out of the 3 steps is that identify the direction of the increasing flux in the core through the coils. Step number one. Step number two, excuse me, let me drink first. Step number two, use the right-hand rule to determine the direction of current into the coil, which causes flux opposing the one that you determined from number one, the original flux. And then number three, positive polarity of the induced voltage occurs on the terminal from which the current into leaves the coil. Okay, so those are the three steps that I summarized from Lenz's law. Right, let's look at an example here. Okay, from this example, let's say that the flux is increasing downward. Right, there's the core. Yeah, this is our magnetic core, and the flux inside the core is increasing downward. So that's step number one, right? Identifying where the flux in the core is increasing, right? That's increasing in the downward direction, okay? And now, part number two, determine the direction of the current injected into the coil from which we get a flux that is opposing the original flux. Here is our original flux, right? And the direction is downward. So therefore, in order to cancel that or oppose that flux, I need the flux that goes upward, right? So if you look at this coil, right, what kind of current or what direction of the current would produce flux that goes upward? Right? Here's the coil, right? I pretend the arrow is not there, right? So all you have is a coil. And the coil, as you can see, goes in and out, right? So go ahead and use your right-hand rule. And you can see that in order to produce flux that is going upward, current has to flow into the top terminal of the coil. If you do that, go ahead and do the right-hand rule. Then you get flux that is going upward, right? Okay, to oppose the original flux. That's step number two. Step number three is what? Step number three states that the positive polarity of the induced voltage happens when the current leaves, right, the coil. So the current leaves, is that right? Just double checking. Come on. That's it again. Sorry about this. Number three, positive polarity occurs from which the current is leaving. Okay. So when the current leaves the coil, that's why we have the positive polarity of the induced voltage. As you can see, if the current enters from the top terminal of the coil, then it must leave from the bottom terminal of the coil, right? So therefore, the bottom terminal should be our positive, should be the positive polarity of the induced voltage. Okay. Any questions on this? Okay. If not, then I'll let you do the next example yourself. Let's see if you agree with the answer I have there. Okay. Let me know if I have a typo in that answer for the second example. All right, next, magnetic properties in free space. First thing first, units for magnetics, and I'll tell you from my experience, okay, that one of the things that makes it challenging for us to design components, magnetic components, are units. The units, different companies, they mix up different units, gets confusing, sometimes. Well, not sometimes, oftentimes, I should say. So again, based on my experience, yeah, you got to be careful. Some data sheet of magnetic cores will give you units in CGS instead of SI or MKS. Right? This is SI unit, right? I believe, right? That's the CGS unit, right? So I just have to be careful, okay? Then you have to go back and forth when you're doing the calculation. Imagine that, right? If the units are mixed up, then make sure that you you are consistent in the design equation. You either pick the CGS or MKS, right? Yeah, that's one of the things, and you'll see when we go through different chapters in this book that sometimes, we get confused. I got confused in the past as well in terms of the constant, right? The constant changes. Oh, why is the constant different now? Oh, it turned out to be that this constant is using, CGS instead of MKS, right? That kind of thing. Very hard to keep track of, if we don't pay attention to the units. So I can tell you right away that this will be one of the challenges in designing magnetic components. Okay, so that's why you need to pay attention to units, and that's why I decided to include this in the book so that you have the reference in the future in case you need to do a conversion between unit MKS to CGS, right? So anyhow, just a couple of examples. H is field strength, right? MKS is amps per meter, but in CGS they use Oersted, right? Flux density, they use Tesla for MKS, but then we use Gauss for CGS. Okay. So yeah, make sure that you go back to this table, right? If you see a data sheet and then they give you these different type of units, right? And you can easily forget this, right? Is Maxwell CGS or MKS, right? Is let's see, Tesla, right? Is Tesla MKS or CGS, right? So sometimes you need to know. It's just I think it's just better for you to have this table just to verify or make sure that you are working on the same units, right? On the same system of units. Okay. And the next table shows you the conversion, right, between one to the other. Okay. Between Weber and Maxwell, amps per meter to Oersted, and so on and so forth. Okay. Gilbert, there's another unit right there, Gilbert. Instead of amperes turn, they use Gilbert for CGS. Okay. Oh, look at permeability of free space. In MKS, we use Henrys per meter, and that's the constant that we saw earlier, 4 pi times 10 to the minus 7. But if you use CGS, it's just going to be 1 and dimensionless, right? Okay, so you need to pay attention to the units. Okay, that's that for the units. And then as we saw before, that magnetic field lines around a long wire which carries an electric current form concentric circles around the wire. The direction of magnetic field follows the right-hand rule. We all know that already, and it is perpendicular to the wire. I won't go through that anymore. Come on. Right. So right there, we already know this, right? Magnetic field around. Maybe I should use this. Maybe that's why it's jumping around. Okay, that's how you would determine the magnetic field around a wire. And then the magnetic field strength, we also learned this from the previous section, right? No, not previous section, but sometime earlier. That magnetic field intensity is equal to HDL integral, closed loop integral of HDL. This one is correct, it's DL. Is equal to I net, and H is, the circumference of a circle is 2 pi r, right? That's equal to I net, which is I in this example. And so therefore field intensity is equal to I over 2 pi r, right? That's actually per given distance from the wire. Okay. When the current I is reversed, the magnetic field H will follow the current reversal per right-hand rule, right? So it's gonna change the direction of the field accordingly. And again, this is if you wire, if you form a coil with the wire, then you have magnetic field that is concentrated inside the core, as we discussed earlier. And actually, I have this that mimics, a bar magnet, right? As we discussed earlier. So let's skip that because we discussed that already. The magnitude of the flux depends on the product of current I and the number of turns N in the coil, so N times I. The force Ni, so the product, okay, the product Ni is called magnetomotive force, MMF, right? The flux has density whose symbol is B, as we already learned earlier. Relationship between B and H is equal to mu, right? So B is equal to mu H. The ratio of B over H is equal to mu, right? And that's the slope of the curve if you graph, B against H, then the slope gives you the mu, right? Permeability, right? And again, we call that for free space, mu r is equal to 1, and mu naught is equal to 4 pi 10 to the minus 7 if it's an SI or MKS system. And I think I also mentioned this earlier that 4 pi times 10 to the minus 7 is equal to roughly 1 over 800,000, right? So here is the function, right? Take a look at this function. It is a simple function, but I want you to take a look at this one, right? That for air, air is pretty close to free space, right? So free space close to air, but the equation for flux density B with respect to intensity is equal to 1 over 800,000 H, right? Go ahead, if you picture this in your head, or I can just draw it here, right? If I were to draw this, right, graph it, right, B with respect to H, right? 1 over 800,000, that's pretty much a flat line, isn't it, right? It's pretty much very flat, right? It's almost like a flat line. Maybe that's too much, like that, right? So for a change of 1 in the x-axis, in the y-axis, you have to change 800,000 times, right? That's what it means, right? So it's pretty flat, isn't it, right? If you draw these, field density with respect to field intensity of air or free space. Again, I'm assuming that air is going to be very close to free space, right? Okay, so then increasing MMF by increasing I or N results in increasing field, right, from this equation, right? If you increase, remember, H is Ni, MMF, sorry, H is Ni over L, but MMF by itself is N times I. So if you want to increase the field density, then you could do that by increasing I or increasing N, right? And then if you use free space or air, then the core theoretically would never saturate, right? You can keep increasing. Here's the graph right here, right? I have it right here. So B is in milli Tesla, and H is already in amps, right? So this is 800 amps. So what it means is that in order to produce 1 millitesla, you have to have current of 800 amps per meter. That's a lot, isn't it? Right? And yes, you could theoretically increase the current, right? Go ahead and increase the current to 1,000, 2,000, 5,000. And theoretically speaking, the flux density is going to increase linearly following this graph, right? Okay. But there are two things that are a problem here, right? There are two things that are problematic here. What's the first one? Well, the first one is that that's too much energy. Too much energy to create, this small field, density, flux density, right? You need 800 amps just to create 1 millitesla. If you use air, right? If you use air as the core, or free space as the core, or vacuum as the core, right? That's the problem with it, right? For some application, using air core could be acceptable, but definitely not power application. Maybe for communication type of application where power is not a concern, for example, right? Then you could definitely use air core, right? And again, one advantage of air core is that it doesn't saturate. But again, the practical issue with this is that it's too much energy to create small flux, basically, small magnetic field, basically, right? Too much. That's number one. Now, even if you can create the energy, then don't forget that this amperage has to go through wire. So the other practical issue would be temperature. Right? Imagine you have to have a coil, right, around air or free space or vacuum. And imagine if you inject 800 amps, right, just to produce 1 millitesla. What do you think is going to happen with this wire? Hot, of course, right? Because each wire will have resistance. So that's another practical issue with these free space or air core, right? That's why we don't usually do that, right? That's why for most applications, we don't use air core. It's gonna require too much energy to create the field, right? To create magnetic flux, okay? It's basically, at the end of the day, we care about inductance, right? So I keep talking about flux or field, but at the end of the day, what we want is inductance, right? So this means that in order to create a certain inductance, inductance is actually proportional to the slope, right? You're going to have so much currents, right, to create small inductance, basically. Right, so I think that will be more relevant to us, right? If I speak of inductance, right? To create very small inductance, you get 800 amps. That to me is not really worth it, right? Especially for power application, that's not going to happen, right? It's not efficient, and you got high temperature on the current as well, on the wire. Okay. All right. How much? Oh, it's 2:59 already. Oh my gosh. It's 3 o'clock. All right, let's finish this. How much H is needed to produce 1 millitesla in free space? I already told you that, right? From BH curve, the H required to produce 1 millitesla is approximately 800 amps per meter. Yeah, good luck with that. Using 800 amps. So non-magnetic materials such as air, copper, paper, rubber have BH curves almost identical to that of free space, right? Okay. And then if you use AC, right? So then the flux excursion is going to be positive, negative, then the curve will transform into this type of graph right here. So it's not just the quadrant 1, but also you're going to use quadrant number 3. Okay. All right, I think that will be it for today. Let's see. Yeah, let's just stop right there. But before I stop, if you look at BH curve of a magnetic material, when it goes into saturation right there, guess what? The slope of this region where it saturates should be equal to the slope of what? Based on what we learned.
Free space air.
Exactly. That's why it's really flat, right? When you saturate, then the slope is pretty much flat because that's 1/800,000. Right? Basically, that's the slope of air or of free space. Okay. Now, basically, your magnetic material becomes air. If you operate the core here, then you basically using the core, using the magnetic material, expensive magnetic material as an air. It's just similar to air, right? Or free space, right? So useless. Okay. So you're wasting money because of that. All right, enough.